Welcome to today's lecture on the importance of test datasets and data splitting in machine learning. One of the most fundamental aspects of training a model is ensuring that it can generalize well to new, unseen data. If a model is only evaluated on the data it was trained on, we may get the false impression that it performs exceptionally well. However, in reality, it might just be memorizing patterns rather than actually learning. This is why we need to split our dataset into different parts: training, validation, and test sets, to ensure that our model is evaluated fairly and performs effectively in real-world scenarios. Imagine you are preparing for an important exam. If you only practice by repeatedly solving the same set of problems, you might score well during practice but struggle when faced with new problems on the actual test. Similarly, machine learning models need exposure to new, unseen data to truly measure how well they can generalize. A proper data splitting strategy ensures that the model is evaluated on unbiased data, reducing the risk of overfitting and allowing us to assess its real performance. Today, we will discuss the importance of data splitting, explore various methods of partitioning datasets, and conduct practical exercises to observe how different splits affect model performance. A dataset in machine learning is typically divided into three parts: the training set, the validation set, and the test set. Each of these subsets serves a unique role in the process of developing an effective machine learning model. The training set is the portion of data used to teach the model. During this phase, the model learns patterns and relationships between input features and the target variable. This is where the majority of the data is used because a well-trained model requires sufficient examples to capture patterns effectively. Typically, 60 to 80% of the entire dataset is allocated for training. The validation set plays a crucial role in tuning the model. It is used to fine-tune hyperparameters and make decisions about the model's architecture. The validation set is distinct from the training data to ensure that the model is not overfitting to the data it has already seen. Overfitting occurs when the model memorizes patterns from the training data but fails to generalize to new data. By using a validation set, we can compare different models and choose the one that performs best on unseen examples. A common approach is to allocate around 10 to 20% of the data for validation. The test set is the final evaluation tool. It is used only once, after the training and validation phases are complete. The purpose of the test set is to provide an unbiased estimate of the model's performance on completely new data. This is the closest representation of how the model would behave in real-world scenarios. Like the validation set, the test set typically comprises around 10 to 20% of the dataset. The key difference is that the test set should never be used during training or model selection, as this would lead to misleading performance metrics. One of the most common ways to split data is the 80-20th rule, where 80% of the data is used for training and 20% for testing. This method is simple and works well when there is a sufficient amount of data. However, in cases where hyperparameter tuning is needed, an additional validation set is introduced, leading to a 70-15-15 split. The proportion of each split may vary depending on the dataset size and complexity of the problem. Apart from standard splits, there are alternative techniques such as k-fold cross-validation. This method is particularly useful when working with small datasets. Instead of having a fixed validation set, k-fold cross-validation divides the data into multiple folds, training the model on different subsets while using the remaining portions for validation. This helps in obtaining a more robust performance estimate by averaging results across multiple iterations. Another important technique is stratified sampling, which ensures that each subset maintains the same class distribution as the original dataset. This is especially useful for classification problems where certain categories might be underrepresented. If we randomly split a dataset with imbalanced classes, we risk having an unrepresentative training or test set. By using stratified sampling, we make sure that the proportion of each class remains the same across all subsets, leading to better generalization. Now that we understand why data splitting is important, let's perform a practical exercise to see how it impacts model performance. We will start by creating a small dataset and manually splitting it into training and test sets. This will allow us to observe differences in accuracy and understand why it is necessary to evaluate models on separate data. First, we load our dataset. For simplicity, let's assume we have a dataset with two features and a binary classification label. We will use Python's pandas library to create a small dataset and inspect its structure. Once we have the data, we will divide it into two subsets, one for training and one for testing. After splitting the data, we train a basic machine learning model using a simple decision tree classifier. The goal is to understand how the model performs on training data versus test data. If the model achieves a very high accuracy on the training set but performs poorly on the test set, this indicates overfitting. Conversely, if the performance is consistent across both sets, it means the model is generalizing well. To further explore the impact of data splitting, we will experiment with different split ratios. By changing the test size to 10 or 30%, we can observe how the amount of available training data affects the model's ability to learn patterns. If too little data is allocated for training, the model may not have enough examples to learn effectively. On the other hand, if the test set is too small, the evaluation results may not be reliable. Another aspect we will explore is the effect of randomization in data splitting. If we do not randomly shuffle the data before splitting, we may introduce bias in our training and test sets. For example, if the dataset is sorted in a particular order, such as by time or category, splitting without shuffling could lead to subsets that do not properly represent the overall data distribution. This can result in misleading evaluations and poor model generalization. Now that we have seen how different data splitting strategies impact model performance, let's reflect on some key questions. What happens if we accidentally use the test set during training? This would lead to overfitting because the model would have prior knowledge of the test examples, resulting in inflated performance scores that do not reflect real-world conditions. How does dataset size influence the ideal split ratio? If we have a small dataset, allocating too much data to the test set may leave insufficient examples for training. In such cases, techniques like k-fold cross-validation become useful. Why is randomness in data splitting crucial? If data is not shuffled before splitting, we risk introducing biases that can distort model evaluation. In summary, the process of splitting data into training, validation, and test sets is a fundamental practice in machine learning. A properly structured split ensures that models learn effectively while being fairly evaluated on unseen data. The validation set plays a key role in tuning hyperparameters and selecting the best model, while the test set provides an unbiased estimate of final model performance. Overfitting can be mitigated through careful splitting, and techniques like stratified sampling help maintain class distributions. Understanding the role of data splitting is crucial for building robust and reliable machine learning models. Without proper data partitioning, models may produce misleading performance metrics, leading to poor real-world application. By following best practices in data splitting and model evaluation, we can develop models that perform consistently and generalize well across different scenarios.